Fantastic. So welcome to yet another algorithm sessions from SE Skills. Today's topic is dynamic programming by Santosh. All yours, Santosh.
Okay. Yeah. Thanks, Vivek. Okay. So you guys are able to see my handout, right?
Yeah, that's right.
Okay. Yeah. So these are the problems what we will be discussing today. Okay. So they are all DP problems, and we have selected these three problems. One is the remove boxes, the strange printer, and the burst balloon. And these problems came up with our daily lead code sessions, and we found out some of them were slightly different. Okay, so now the way I look at these problems is, okay, before that also, what I would do is I would actually walk through the problem, the first problem, as well as its complete implementation, the way I understood it. Okay, and then maybe people can actually give me inputs or suggestions, whatever they can be, and then we can move to the next problem. So why I'm saying that, because this first problem, if we go through the implementation, the same implementation can be used for the second one also. So they are almost similar in implementation. And the third problem is not almost same. It doesn't have a similar implementation of both the two, but on a broad scale, it is some way related to these implementations. So therefore, we have included that. And also, this was not a part of the third one was not a part of our daily lead code sessions, but someone came up with saying, okay, it also looks like to be a part of this similar implementation. That is the reason it is here. Okay, so having said that, also I'm not going to go in basic details about what DP is and how to solve that, like the optimal substructure and overlapping subproblem, because the implementation of these problem itself is slightly more, and it will take more time. It will be more time consuming. So therefore, I will quickly just jump into the problems and how to go about the problems. Okay, so with that, I will first go to my first problem. Okay, so this is the first problem, which is remove boxes. And I think most of the people might be knowing about it who are regularly attending the lead code sessions, the daily lead code sessions. So this problem actually is, it says that we are given several boxes, and they are with different colors, and all these colors are represented by positive numbers. Okay, and then we have to actually go through several rounds. We have to remove a box, okay, or maybe boxes, and each time when we can do that, we can remove a box or a continuous boxes of the same color. Okay, we can always remove a single box of a single color, or we can remove continuous boxes of the same color. So that is the only condition, and therefore it says about k boxes where k will be greater than or equal to 1. And so whenever we remove one box, we score some points, and the points are like k square or k into k. Okay, and our goal is to actually get the maximum points while removing all that. And so they have given an example over here. And then if you look at with the constraints, it says it will, the box will have at least one box, or maximum we can have 100 boxes. And also the colors, they are all positive numbers, so they will start from 1 to maximum 100. And then this is the example. It talks about this is the whole input array, which will be as an input to our function. And this, if we remove, and it's shown here, the output is 23. Yeah, so the output is 23. And the reason why the output is 23, they have explained it here. If you look at the way they are going through is the first, the 3 2s are removed. Okay, and so when you remove 3 2s, you get 3 into 3, which is 9 points. And why we get 3? Because we removed 3 boxes of color 2, correct? And then, so now we are, so it remains that we have this remaining array. And then again, only 1 is removed. Okay, and then again, only 1, which is 4, is removed. And so why it is removed? Because we want to bring all these 3 together. So when you remove a single box, you get just a 1 point, it is 1 into 1. So 1 square is always 1. And then again here, in this next step, all the 3 boxes are removed. Okay, so therefore we get 3 into 3, which is 9 points, and we are remaining only 2 boxes, and then we remove these 2, we get 4 points, and this total adds to the 23, and that is the reason the output is 23 in this case. Okay, so I will actually go through my OneNote. Okay, and I will try to walk through. Okay, so this is the way I was looking at the problem, So I'm taking the same example what they have discussed in the lead code problem. So this is the problem. So if I can solve this problem in many ways. Okay, so one is and I'm specifically putting in 2 cases. Broadly, it will go in 2 cases. One is, the first case will be I will start from the left side to the right side. I'll just go one by one. Okay. So while going one by one, I'll always see if there are any continuous boxes with the same color, and then I will just quickly remove them. But if it is not, then I will just remove a single box. Okay. So now in this case, the first box is 1. Okay. And then I remove that box. So I will get points 1 into 1, and I'm left with this array. Then I remove 3. In this case, I'm going to get 1. And then this array is remaining. And so I remove 2. In this case, I have 3 2s, and therefore I get 9 points over here. And then similarly, I can do for 3 4 3 1, which will be removed one at each time, and therefore the points will be 4. And here, if you see, my total points are only 13. Correct, because I'm doing it from left to right, and I'm doing almost sequentially, but only when I see a group of boxes together, I remove them together. But in the earlier case, like in this case too, what was also explained in the book, so it's not done that way. What is done is we first remove the boxes which are of the same color. Okay, and then this is the way it was done in that problem statement, right? The explanation. But here you get the points which are 22. And why you get that? Because you tend to club all the boxes of same color together. And while doing that, like if you wanted to make all the 3 together, because initially they were not, right? So in that case, so what we had to do, we had to break down the problem like this. So first to solve this particular problem, right? First, just solve these 2, okay? And then could get this one. So now we know that to bring all these 3 together, this 4 is not in sync, so we need to solve this 4. So when we solve this sub problem 4, then we can see that all the 3 are come together. And then at the end, so we can remove these 3 boxes of this color 3, and then we are left with 2. So if we do it this way, we can, if we bring all the boxes of the same color which are separated together, then we get an optimal solution, or we are able to score maximum points, right? So that is the reason I'm saying that we have 2 cases. Okay, one is we don't bother about bringing them together, and the second is we just bring them together. So these are the 2 cases. And to just on a high level, how to represent it. Okay, so this is the way I just picked this figure from some site. And so like if we are given with just an simple input array 1, 2, and 1. So what we could do is we can sequentially start with each and every index, right? If I start from index 0, I follow this path. I can start from index 1 and then follow this path, and then index 3 and follow this path. So if you look at this diagram, so if I start with 1, the left one, and then I remove that box, then I'm remain with 2 and 1. Okay, and then again here I start with the left, which is a 2. I remove 2, and then I'm left with 1. Okay, and then I come to the end, then I return. So when I'm returning, I know that I've just removed one box, so I'm returning one value here. And then from here again, I know that I'll have to return this one along with the one of what I removed for the 2, right? So the answer here will be 2. And if you go this path also, again, the answer is 2. And when I'm returning back, I'll return the maximum of both these values. Okay, and then I'll just add 1 to that because I've removed 3, and then I return that value, which will be 3 for the first index, 0th index, right? And if I do this, if I start from index 1, okay, so if I remove 2, then you can see that this 1, 1 are together, right? I hope you're able to see the screen and everything, right?
Yes.
Okay. So if I remove this 2 in this case, right? So you can see that I was able to get these 1, 1 together, right? And then when I actually remove these 2, which are of the same color, so the output what I will be returning will be 4 because they are the 2 boxes, right? And then at the end, if I come here for this index 1, the return value is 5 in that case. And if I follow this, the last one, it also returns value 3. So actually what we are trying to do here is in this first 2, we are following the case 1, right? So this is like the case 1, and this in this one, we are following the case 2. So we are also following the case 1. So what does that case 1 and case 2 are, like I'm just trying to explain it here. So same way. So if I'm taking another example, like if this is my input, so what does the case 1 mean is I just count all, like count will be my k. I'll count all the same colored boxes which are already grouped together. So in this case, my starting box is of color 1. So I just count for 1. Okay, in this case, they are 2, and therefore my k value is 2. And then I remove those initial boxes of those color 1. So my array remains this one. So this is my remaining boxes, right? So if I solve this problem using the way it was represented above, so if I solve it using a sort of a DFS, so I just first I take the k, square it, and then just put this remaining boxes into DFS, and then keep on doing it recursively. So I'll get some answer, right? So that is what we did for the case 1. And in this second, now as you see, so when we are with this remaining boxes, so we know that we started with the starting box of color 1. So how actually we would like to take care of this, or maybe implement this case 2 is we need to start bringing all the same colored boxes together. And in order to do that, so we need to start traversing again this array. And when we are traversing this array, we need to look out for whenever we find a box of the same color as the starting box color, right? So if we find that, we just stop over there, and then we break this group into 2 groups. Okay, so the first group will be all the boxes before the start box color. Okay, and the second will be like starting from this again the start box color, which was 1, and along with all whatever the remaining ones. So we are actually breaking this input group into 2 groups, group 1 and 2, and they are like the sub problems, and then we solve both of these sub problems here. And so whatever we get, we add that value, and then we get an answer. Okay, and so out of this, Okay, so whatever is the maximum value, okay, from these two we return. And obviously we have to do this for each and every index, right? So if we start from 1, so similarly we go for 2, then we go for 3, then again for these 1 and 5, 6, and we keep on looking for both these two cases. Okay, so if we are able to go through this, then we will be able to find an optimal solution to our problem. Is this clear? Or you want some more explanation about this?
I have a question.
Yeah, sure.
Whatever you have explained is clear, but don't you think like case 2 will always give you the max answer?
Well, yeah, that's a good one. So, okay, so I'll just show you one thing. Why the case 1 is also important. So in case if we have something like this, okay, so we don't have any repetitions of the 1 anywhere else, or all of them are unique, but they are close together. If there is repetition, they are together. So in this case, so you will always, this case 1 will always be satisfied. So you don't have to go to case 2 at all, right?
So what I'm trying to say is your case 2 will still give you the same answer as case 1 in this case. So I'm just trying to figure out why do you need to have two cases? If you like always group it and just proceed that way, I think case 1 answer will, will work out.
Well, okay. So things will be more clear when I show you the implementation, why I'm saying that.
All right.
But still, I would like to answer your question, So one is like, if we have all the unique colors, okay, so you will always come out from case 1. And also, always, if you look at it, I'm always adding my whatever that points only at the case 1. I'm not adding them in the case 2 at all. So even if I'm going to case 2, I'm just trying to break down the problem, but eventually it will still go in the case 1 and come out. So it will always go and do that. And also the reason why we have to break down is when we know that we have a k value here because of these first ones, and then this k value also, when we are actually grouping them, I have to pass that k value as another parameter. So this will be an additional information that I'm going to pass. Okay. So when I come back on the recursion, again, I'll come here, right? So at that time I know, because my initial box is always the first one, and it will look for k. If there is a value of k, it will start incrementing from that. And that is the way it is trying to bring them together. Right. So that is the reason actually the both cases are important.
Yeah, okay. I guess when I see the code, maybe I'll be able to understand.
Sure, absolutely, yeah. But yeah, in a high level, it is, yeah, go ahead, Arshad.
Yeah, and just to add, I think in case 2, we are taking care of the non-contiguous occurrences of a particular color, right?
Case 2 is more about contiguous, right?
I think case 1 is about contiguous.
No.
So it's like, when we have all these same colored boxes together, okay, so then this case 1 is fine. But when we want to bring this 1, 1 and 1, 1 together, so we have to take help of case 2. So we bring them together, and at the end, when we want to count them as a complete consolidation of k, then we come to case 1, and then we add that value to our answer.
Right, absolutely.
Yeah.
So are we allowed to sorting, Santosh?
No, actually, because it's the order matters, right?
Yeah.
Order matters here, and they have not said that way. They just say you remove the boxes, because if we do sorting, it will be easier problem, right? Right.
So at every point you're comparing with your start index, right? But what if my group of numbers was bigger somewhere near the middle? Like how are you getting this as your intuition? That you have to split it like this. I would have thought this is greedy. I would try to see which is the maximum number. I would count the number of ones I have. I would count the number of twos I have, and then club accordingly, right?
Yeah, so yeah, that is true, but still, okay, that is good way of thinking. but you still have to explore all the possibilities, right? So that is what we have to do. So now I'm just looking for 1. So we might have something like it will be 1 1 2 2 3 3, all of them are repeated. So it might be the optimum solution will be at, if I bring all the 2 together and not bring all the 1s, right? So there might be a test case like that also, right? So it might be something like 1 1 1, but still have 2s 2 2, and then something like 3 3. But if you look at predominantly, my 2s might be much influential in that case,
Yeah.
right?
Yeah.
So I have to always go through each and every one. So I start with 1 for sure, okay? Then I complete the whole, the way we have done over here. And so I have to go for each and every index, explore each and every one, and then only I'll be able to get an optimal solution.
Cool. Okay, thanks.
Yeah.
So just one more clarity. Can you scroll down?
Yeah, sure.
Okay. So for the case 1, you start with index 1, and there you see that you have like 2 1s clubbed together. So that will be, you're just going to club them together and try to get the result. Okay. For case 2, you're saying bring the same colored boxes before the start color 2 3 group.
Yeah.
So how do you scan it, and how do you, like, what is the process there?
Right. So when I know, I will always have this start box color, okay, which is at index 0. And now I've remained, I'm with these boxes. Actually, I'm not actually breaking down here, but it's only the index which I'm at here. So this index might be like a 2. So I'm at index 2. So I will start scanning from index 2 all the way to n.
Okay.
So as soon as I find the first index where I see a same color of the start color, I break.
Okay.
Okay, I just break that and then break this into 2 groups. So I just make this one as one group, okay, and this is the other one as a 2 group, and then again pass that in my same DFS. But when I'm passing the first 2 3, I know that it doesn't have 1.
Right.
Okay, so therefore this k value will be as 0, because I want to start this group as a fresh group.
Okay.
But for this one, I know that I'm going to pass 1 as a start index, which is same as what. So therefore, as the value of k. So when I come back on this again here, so I know in this case my k is 1, so k is 2. So I can start from here and just count k will be 3 and k will be 4. So automatically they are grouped together, and here it will be like, instead of 2 2, it will be 4 4 plus, and the remaining boxes will be just 5 6. So that is the way I'll solve.
Okay. So I think I think DFS group 1 shouldn't be 0, because it should be the correct index, right?
Well, this is yeah. So anyway, I'm just abstracting this, but I'll have more parameters to pass. But I'm showing only the important ones here, and that is the reason I'm just showing here the k and the group. So the group will consist of the start index and the end index also, because you are going to have these, right? And I don't want to break the array, Yeah. So I can do that also. So yeah. So the way the brute force way I would implement is, the way it is being discussed here. Okay. So go through an input array, and at any time when I see one box, just remove that box, and whatever is that array, shrink that array, and again pass to the DFS, and then keep on doing it. So that will be a brute force way. So I'll just show you the brute force for now. And sorry, I just came back here. Okay, so the brute force implementation, even though it's not the most good one and not efficient one, so it's worth discussing here, because you get the boxes over here, and then you start iterating through each and every index. Okay, so if I start with the 0th index, and then I collect all the boxes of the same color over here. okay, and I just increment this count of j, and I is my start index, and j is the index where actually I'm just counting how many same colored boxes are. And then I shrink in the sense I just collect whatever the boxes are remaining, because I want to remove the same colored boxes are the same as the index I, right? So therefore I just shrink them. So I just collect them in remaining box over here and then pass to my helper function. Okay, and at that time I just multiply this by k plus k into k. Okay, and so this also works. Okay, so though it's a brute force and I don't have to take care of the one what we discussed, case 1 and case 2 here, because it will automatically be done over here, and this will also work. But only this implementation actually is more of a, what you say, n factorial in the time complexity, because you have to keep on doing for each and every time. Okay, and also the space complexity. In addition, you have these remain boxes, whatever you're creating always for each and every iteration, each recursion also, right? So this is the brute force. But if you slightly modify this brute force for the way I was discussing about the case 1 and case 2, okay, so here it's still recursion and nothing to do with the DP approaches. Okay, I'm just trying to establish a recurrence relationship. Okay, so if you look at, okay, I'm just coming for this helper function. So this is my entry function, remove boxes, and I'm having these boxes as my input. I just calculate the n, and this helper function, which will be used for this recursion and the DP solutions. So this will be my I. I'll start with this index, and this will be my j, which will be the end of this size. And this is a k for now. So k is 0 because it's a fresh start. And so the implementation for this one is like, this is a base case, because you never want to have a start point greater than the end point, right? And here actually you just club all the ones which are closer to each other, right? So once you have that, that is your k value. Okay, and then so this is the case 1. So case 1 is like, you just whatever you have that k, I'm adding it 1 because the k is also based on index 0. Okay, so this into this, and then we have this helper function, and at the time I'm just moving my I to the next position, and then passing the j will still be the same, and the k will be 0 in this case. So this is my case 1. But, and this will go on recursively to the end. But then for case 2, so again I will start, okay, from, because I've already moved my I also here, right? So now my I is pointing to almost at the end of my same colored boxes. So I have to go past that value. So want to compare, okay, the remaining boxes and try to find if I see any box, okay, which is the same as my start color box, and which is the start color box is the index I. So as soon as I find, then I break them into 2 groups. So one group will be like I minus 1, and m minus 1 is the current pointer. So where I'm trying to break, okay, and then this one will be whatever the remaining, and here this guy will have the start index also as the same one here, and it will end at j, and that is the reason I will be passing k's value to this guy also. Okay, so when this is passed, actually it comes back here, and then I'm able to increment my k over here. So that is the way they are brought close to each other. Okay, I hope this makes a bit clear about what I was talking about, case 1 and case 2. Any questions on this?
One thing, Santosh.
Mm-hmm.
In line number 51, should it be I plus 1 to m, then m plus 1 to j?
Okay, so, okay, let me take a test case, so things will be more clear. So this is like you have 1, 1, so we have 2, 3, 1, 1, 4, and 5, right? So in this, my Okay, the first thing, my I will be some 0. Okay, and my J will be 1, 2,
7.
3, 4, 5, 6, 7. Okay, 7. And so if you see here, K initially was 0. So K will be incremented. Okay, so I'm comparing I, okay, with I plus 1 always. Okay, so I'm just trying to compare. So the K will be 0 and 1 in this case, right? So when I come here, my K will be just 1. Okay, and then here actually it will be 2 into 2, and then whatever that recurrence relationship, right?
Yeah.
So yeah, it will be like I. Now in this case, if you look at this I, okay, so I was 0 here. Okay, so it found here, so it is 1. Okay, so I will still remain at 1, right? So
Okay.
here my I will just be at 1. It's not going to go to 2. Okay, so therefore when I come to this case 2, okay, so I start from I have to start from this one, right? So therefore I'm just incrementing it. So M will start from 2 to 7, correct? And then I'm
So
always comparing.
I think I would be 2, because when 1 and 2 would be compared, it would be true, right? And then it would move to 2, and then it will break at 2 comma 3.
No, so I is 0, okay? So I will
Okay.
be start with 0, and so it's going to compare 0 with 1, okay?
Okay, I got it.
So this will be 1, and then when I go for this one, when my I is 1 and I plus 1 is at 2, right? So then it will break, and that is the reason I will be at 1.
Yeah.
Okay, so then from here it will be M2 to 7, and then when I see they are this 2 value, this 2 actually is not the same as 1, right? Okay, so when this value like this 2, 3, 4, okay, so when my M is 4, then I'm going to break. Right, so when M is 4, it has 1 value. Okay, so then it is comparing with this one, so then I'm going to break, and that is the reason. So if you look at I plus 1 in the first group, so the group 1, so I will be 2 and M minus 1 will be 3. And if you look at this is the 2 and this is 3, so therefore I'm breaking into, so okay, these are indexes. Unfortunately they are also almost the same, right?
Yeah.
So indexes. So these are the indexes, and the values are also for the group 1. So the group 1 values are 2 and 3, right? And
Yeah.
then if you look for, so M, which starts from 4, so it will be like 1, 4, 5. So my second group will be, so this group 2 will be 1, 1, 4, 5, right? So 1, 1, 4, and 5. And this group will be passed to this helper function along with this k value, and this group which is 2, 3, which doesn't have 1, so this will be passed to this helper along with just resetting the k to 0. Okay.
Yeah.
And so this will keep on going, and then we'll be able to get, but this will also pass many test cases, but as being it will TLE on some big ones, and therefore we have to take help of some top-down approach and all that. Okay, so if I do add a memoization to this, okay, so this will be a top-down approach. Okay, so I'm just adding a memoization, and in memoization I'm actually having I have to take a 3-dimensional array. Okay, because I have to store I, J, and K. Okay. So in this case, I come here, this is my memo, and everything remains same. The base case is the same. And look for the memo. If my value is not equal to -1, I return whatever is in there. And this is the same one. Okay, this is my case 1. And then I come here and do for the case 2. Okay, and then I just store my results here in the memo in the cache, right? And then I return. So this is a top-down approach for this problem. I hope it is at least some way it's slightly clear at least, right? Because for me it took a time to understand this, so I had to go through a lot many times to understand that. But in a nutshell, it is like if you are able to break down the problem into case one and case two, and the case one, case two, if you implement this way, okay, and most of the implementation, like if you look for those matrix multiplication type of problems, right, uh, for a DP, so they are sort of similar, okay. I won't say same, but they are similar, right? Yeah.
So Santosh, what does the state I and J and K denote for you in this code?
Okay, state I and J is like the start and end of the current boxes, what I'm looking for. Okay, so I'm interested in only I and J, means this boxes I'm not changing. I'm not actually shrinking my box array, but I want to look at a problem space, which I am more interested for now, because I'm dividing this always, right? When I go to this two helper functions here, I'm dividing my problem. So when I'm dividing, I have to, these are the start and end points of that, what I have to look for. Okay. And then K is the repetition. So what I have been repeating for this color at index I. Okay. So that is what K means.
Got it. Makes sense.
Yeah. So if, yeah. Yeah.
Hey, can
Good.
you go back to your brute force 1 second, like the previous solution? So in this, like, okay, I start with one set, right? Like say I like all the ones. So in that case, my K becomes 2, and like later you see for more one boxes and your K keeps incrementing accordingly. But then in the meantime, if I see that, okay, I got 4 boxes of 2, like where is that being taken care of here? How are you going about it? Like, because we're not storing anything here, right?
Well, this, okay, so this is the recursion, right? Okay. So when I'm done with this, okay. So this is my remaining boxes. Okay. So then it is going in this helper function. Okay. So at least you follow one thing, right? It keeps on going from
Yes.
here, right? And then it goes to these, right? So when you are done with this, so this helper function will come again, and then it will come to this place, right? So then it will keep on dividing that. So you'll go follow for this one also.
Yeah, but like in your memoization solution, like you're actually maintaining, right? Like for this box, these are the number of K I've already seen.
Well,
but
here also I do this, right? So this is the K plus 1. And here is the one what I'm actually. So the memoirs and this one, they are the same. I'm just adding memoization over here. I use the same one.
yeah.
So what is not clear for you?
Like let's say it was 1 1 2 2 3 1 1 2 again, right? So we would want to probably club those twos also at some point.
So it is 1 1
2
2
3
3
1 1
1 1
2 2
and 2 2, right? Okay.
Yeah.
So I'll just remove this. Okay. So here in this case, my this again, I will be the same 1. So K will also be 1, right? So now when you go to this 2 case, okay, so what I'll be having is 2, right? Then 3, okay. So then 1 1 and 2, sorry. So yeah, 2 and 2, right? Exactly. So when I go to this helper, so see, okay, even if, so now the one case is being taken care of, correct? Here, okay. So it's going in one path. But now if you see, you can freshly start this 2 3 1 1 2, okay, on your own with this helper function. Okay, so then you come again here So when you come for the next time, okay, you will have, okay. So when you come back, okay, so at that time you will have this as an input, right,
Yeah.
over here. So if you can just override this guy,
Yeah.
okay, so you will have this. Then you can start from 2 from here as a fresh one.
Okay. Okay.
So that will be taken care of recursion.
Yeah.
At
Yeah.
the
Yeah.
same
The
See,
time,
I mean,
Mhm. Yeah,
sorry to
Vishal, go ahead.
interrupt,
No
but
problem.
okay, the logic what I see here is like you have two choices, right? Either you find a contiguous, let's say you have some function which tells you whether at this index I'm seeing a contiguous number, assume, right? You have that function. And so once that function returns you, yes, I see something contiguous, and that's when you decide, okay, you know what, whatever is there before this index, I need to treat it separately, and whatever is there after this index, I need to treat it separately, correct? So case 2, he has the max of 2 cases, right? That's what is taking care of that.
Yeah.
And the first very case, what now? It's just like when you want to build a valid parenthesis, you cannot start with a closed bracket, correct? You cannot start with a closed bracket. Similarly here, what if you start with a contiguous number, right? Then you have to need to take care of that. That kind of forms like one of your cases to handle for case 2 too, right? When you're going to case 2, you will fall back to case 1 where you expect things to be contiguous.
Yeah. So they are both hand in hand, even if I'm explaining it separately, but both
Yeah,
are
yeah,
actually
yeah.
together. And it was very hard for me to understand, so I just kept on reading, and then I found all these
Yeah.
things somewhere, and that is the reason I'm okay.
Cool. Thanks.
Okay, so this was the top-down approach. Okay, and it also works well, no issues, and in some cases it's much better also. So if we just discuss how the bottom-up approach will be, okay, for that I will just go to one of my, I'll just share. Okay, okay. So can you see my notepad?
Yep.
Okay. So if I have an input something like this 1 to 1, okay. So now if the bottom-up approach will be different, right? So we'll have to have another 3-dimensional array. Okay. So now it's like we have 3 elements in it. Okay. So we'll have to have a 3 by 3. So it will be 3 by 3 by 3. Okay. So this will be my DPA, and this is the DPA array. Okay. And in this DP array, if you see this, the first one will be the rows, which will be I, and the second one will be the J, and the third will be the case. Okay. So if you look at this one, so the top 0, 1, 2, 3, I'm representing the column index, and the ones which are here, okay, so the 0, 1, 2, 3 here, they are the row index. Okay. And here they are all the case. So I'm showing all these 3 case together. So 1, 2, 3, 1, 2, 3, 1, 2, 3, and all that. Okay. So I think this is clear, right? And so now for the top-down approach, what we have to do is we actually go diagonally, right? So we actually fill all the diagonal elements first. Okay. So now the first thing what we have to do, this is the base case, we have to actually just go and fill out. So we know like this is index 1. So if at this index 1, we can't have more than 1 repetition. So k can be maximum be only 1, right? But if you go for 2, okay, we know that this can also, this will be 2, it will be 1 itself because we have no repetition. But there can be another repetition over here, okay, so that we can have first element as 2. So we can have 2 2s. So therefore, for this particular location, I can have k as 1 or k as 2, right? So therefore, my k value I'm trying to represent here. So the first one I will have just k1. So for the second one, I will have k1, and the k, if the k's value is 2, the multiplication or the squaring will be 4, right? So therefore, I have to initialize this to 4. And for the third one, I can have 3 cases. So one is either k will be 1, or the k will be 2, which will be 2 into 2, or k will be 3 into 3. So I have to actually initialize these three values, okay? And then I start doing the normal way, right? Okay, so now so first I do for length is equal to 1, okay? If I say length is equal to 1, then I say I starts from 0 and j will start from 1, okay? And in this case, as I is 0, okay, so my k will always be 0, okay? Means I'll have a single k. So my 0 and 1, so I'm just looking for 0 and 1. So 0 and 1 lies over here. So I need to actually fill up this location. So for doing that, what I do is I have to again go via two cases. Okay, so if I follow the case 1, okay, so the case 1 will be very simple, right? If I am at 0, 1, I have to find the 0, 1 and the k 0 value, okay, because k will always be 0 in this case. So I need to go and look for the previous values what were calculated for that, okay. So the previous value will be so it will be I will be 1 and j will be 1. So in that case, whatever is at this location 110, okay, so if it is something like dp of 1, I is 1, j is 1, and this is 0. So this plus 1, because there is no repetition in this case, right? My 2 is not same as the first index. So I can say they both are separate. So I just have this case 1 where I just add 1 to my previous results. The previous results are already calculated over here, right? So this is my base case, what I did. So if I add 1 and 1, so my answer will be 2. Okay. So because this is only case 1, we don't have a case 2 in this case because this 2 is not same as 1. Okay. The same thing I do for the second in the length 1. I just increment I to 1 and then j will be 2. Okay. And in this case, I will have two case. One will be 0 and other will be 1. Okay. So now I'm actually trying to fill in this value. Okay. So it is at 1 row and 2 column. So here you see I've actually filled in 2 Ks. So for the first K will be the same thing. Okay. So I go look off for the previous one, 1 row below the same column, and then just add to that. So this will be the 2 value in this case. Okay. And but then what I do is, okay. So this is 2 and 1. So here also now in this case 2 is I 2 I is 1. Okay, so I will always look for this one 1 and 2. So they both are not same. Okay, so in that case, so this value will be 2 here. Okay, and then when I go for the second one, okay, so second K, so which is 1 here. So when I'm saying, what does this mean? You know, like my this previous value, okay, for this one, if this is 2, okay, they are not same. But what if my 2 value is also 2 in this case? Okay, so this will be 4, but this value is only 1, right? So I know that there is another value which might be same as my I value. So that reason I have to fill in this K value also. Okay, for that what I do is here as we had just 1 into 1. So in that case I will have K will be 2. Okay, because I have to take care of in case if there is something which is same as the current I, which is previously which is not seen to me, but I know that this my index is not 0. So my index is something else which is more than 0. So I have to take care of all those Ks and I have to keep on filling them. So therefore, I'm just taking if in case if there were 2 2s, okay, so my K will be 2 into 2, but still the previous value, okay, so whatever the previous value was actually 1, because here there is nothing because this is the last value, right? So I'm just taking, so this will be the base case for it, it is 1. And so if I add 1 to 2 by 2, 4, so this will be my 5, sorry. So I've filled in first 2, then I actually go to the last length, which will be 2. And then in this case, I start with 0 index. and then go to j. And for this, if you look, my I starts from 0, so my k will again be only 0. So therefore, I have to just fill in this value, and this will be my result, and this is the value I'll be returning. So in this case, again, I go through all of this. Okay. Yeah. Any questions?
Fine.
Okay. So when I go from 0 to 2, so actually I'm going from here. Okay. So I'm going from 0 to 2. So in that case, what I will be doing to fill this value. Okay. So again, I will have something like an m. Okay. So in this case, m will start from I plus 1, which will be 1, and it will all run to 2. Okay. So it will keep on looking from this value. Okay. This should be 1. Okay. So it will start from this value because this is the I plus 1 value, and then look for this index if I find any duplicates. So for the first value, when I come here, 2, okay, so there is no duplicate, right? Okay, so in that case, it's not going to do anything. But when I come here, when my m is 2, I find this 1 is equal to this 1. So I find 2 ones. Okay, so in that case, okay, so so for that, actually, if you look in this case, so like m is 1, and then this case 2 for that case will be, so okay, so for this one, the case 1 in this case will be just whatever was the previous value, which is 1 2 1 2 and 0, right? So this will be my plus 1 into 1, right? So that is very straightforward. And so for case 2, the value will be, so case 1, the value will be 3. But if I go to case 2, because here the case 2 will also be valid because I have 1 equals this value. So this 1 will be when I'm traversing in the m from 1 to 2. So for the 1, I don't find any duplicates, right? So this is 1. So 2 is not equal to 1. So I won't do anything. But when I come to this part, okay, so this is 2. So I find this 1 is equal to here. And in that case, I actually have to break down into groups, right? So one is I is 1 because it is 0, I plus 1. And then m will be 2 in this case, and 2 minus 1, so it will be 1. Okay, so if I break this way, and then dp of m, which will be 1, and my j will be 2. So if I find this solution, right, so if I look for dp of 1 1, so dp of 1 1, and yeah, obviously here the k will be 0, and in this case the k will be also 0, right? So the k, oh no, so in this case the k will be, because they are same, right? So therefore the k will increase, and therefore the k will be k1. Okay, so if you look at this location, which will be 0 0, so I1 1, so this is the one value. And if you look for this value, which will be I1 2 and the k1 here, so if I add 4 to 1, right, so this value actually will be 1, and this will be 4, and that is the reason I will have a value 5, so which is greater than this case 1 value, and that's the reason this will be 5, and then I will be returning this value. Okay, so this is a bottom-up approach. Is being used by using 3-dimensional metrics. Okay, I will show you the code, but on a higher level, yeah, it is complex to understand also, but basically you are again following the same case 1 and case 2 principle. And then only another more thing is you have to pre-populate all the case for each and every diagonal of these first. So they are actually used up in the calculations of all the values, the higher ups. Okay, so but I just wanted to walk through the whole thing. But it's slightly complex to even explain also sometimes, but that's what the whole thing is. So if we go the bottom-up approach, okay, so, and I can show you, I can print some values also for different test cases. Okay, so here, if you look at the bottom up here, actually, this is my DP array. And then I'm initializing all these base cases with all those 1, 4, 9, and all those values, right? Okay. And then also I found out in case you might feel that why it's not going to overflow. But if you look at the values over here, they're only 100. So 100 into 100 will be like 10,000. So it's not going to overflow. So still we are safe on that front here for this problem at least. And this is the whole top-down approach. So we start from like I was looking for length 1, right? So first I start with the length 1 and then go all the way to n minus 1. And then I start for I just construct I and j based on whatever the length is. So I just assign length to j over here, and then I just calculate I from j by separating the length. So I'll have I and j, and then this is my k. So k, as I said, always will be greater than or equal to I. So k will start from 0th index to maximum I, right? And then this is the case 1 over here, and this is the case 2. So the implementations are almost similar to what they are in the bottom-up approach, but only here we are actually looking for our this DP array and not going recursion. So it's just being done in an iterative way. Okay, and I'm purposely using all those same variable names also to show that they are almost the same, right? But again, here you break for the case 2, you break down into 2 sub problems, okay, and then you pass on the k value for the second one, but you pass a 0 for this value. Okay, so this is what the top-down approach is. Any questions on this?
So how about the time complexity of this DP approach?
You mean to say this bottom-up approach, right?
Bottom up, yeah.
Yeah, time complexity wise, actually, both of them, the Memoized version and this version, bottom up and top down, they are all same. They are like O n cube, right? So n being the number of boxes, okay? Because if you see that we are actually going through 3 loops, right? It looks straightforward here. But also, if you look at this DP array, it's like we are 3-dimensional, and they are all of the same size. So in order to even go and fill in each every one of them, we still need to visit each and every location. That will be n cube, right?
Yeah. Okay.
So that is n cube, and the space is, oh no, sorry, it's not n cube. It will be n raised to 4 because we are doing it n cube, and then we have to go through for each and every one of the index, right? So it will be n4. Sorry, for this it will be n4, n raised to 4, and the space will be n cube.
Okay, space would be O n cube.
Yeah. So
I think it should be n cube only.
Well, this one?
I think both of them, bottom up and top.
No. Both will be n4 because see, this is the first n. Okay, this is the second n. This is the third n, and this is the fourth n.
But essentially what we are doing is we are choosing a sub array and we are partitioning it, right?
Yeah. There might be it, but on a big of n, it will be n raised to 4, right? So yeah, it won't exceed more than n4 for sure, but to some extent it might go closer to that, but not, it will never reach that, I would say. Yeah, see, if you look at this simple problem, so it keeps on making all these steps, and the way I was explaining, okay, and then it keeps on, this value keeps on percolating. So you need all these values, all these ones, and then that is the way it is calculated. Yeah, it's slightly hard to understand also. I was going through it, so it took some time for me to understand each and everything. But on a high level, that is the way it is. You'll have to go through each and every, because I'm also doing exactly the way algorithm is written over here. I'm just going through. So I am just taking a length 1 and then going for I and j the way I was explaining, and then running for each one k. And then when I go for each k, I look for each m, okay, and try to break them and then look for all these values and then add them and come up with that. Okay, so I think that was what I had for this problem. So any questions, any inputs, what you guys have? Or else we can move to the next problem. So the next problem is also similar to this problem. It is, but there are slightly small differences, and it might be, but this was slightly on the, because it has a third dimension of k, right? So that one also has a k in it, but we can optimize that. We can use the same approach. It works very well there also, but it's not that efficient. So we'll have to optimize it. So that is what, so if you look at the second problem, which talks about strange printer. So this is also like you have, it's like the strange printer, right? So we have a printer. What it says, it has special requirements, and the printer can print a sequence of the same characters each time, okay? And whenever it is printing a character, it will print from any position to another position. But whatever it has printed earlier, it will reprint on them, or it will overwrite it. Okay. So if you look at the one, it says that if it is given as a string of English all lower letters, and then your job will be to count the minimum number of turns the printer needs in order to print it. Okay. So there in the previous problem, the remove boxes, okay, though they are almost sort of similar, but if you look at that, here we wanted to find out the maximum, and here we're just finding a minimum. Okay. And in this case, we were trying to find the points, or we were trying to score points which are k square. But in this case, we don't have to do, we just have to find a single turn will be only a value 1, right? So if we have something like this A, B, B, okay, so it will be, it is very straightforward, right? We can actually have these 3 A's together, which will form 1 turn, and 3 B's together, which will form 2 turns. Okay. And if we look for the second, where it is ABA, right? So this will be like, either it will be, so the way it was saying, so first it will start with all the 3 A's. So it's trying to connect here the way we are talking about bringing two similar, two same colors in the previous one together. So it is also doing the same thing, but here it's not bringing them together, but it's adding the same color in between, right? So it's like the same character it's adding. And so therefore we have 3 A's here as a first term. And in the second turn, it is just going to print B on the top of this A, right? So therefore, if you look at it, it's only just 2 turns because we want to find the minimum. Okay, or else it will be like this one. If consider a single turn, then we can consider B as a second turn and C as a third turn, right? So that can be 3 turns also. But here the problem statement says that we need to find the minimum turn. So we want to minimize over here, and there we had to maximize. All right. So that is the reason it's going to be only 2 here. Okay, so they look similar, right?
So why is it printing 3 A's in the first go? Why not just 2 A's?
Where in for the example 2?
Yeah.
Well, actually, see, we cannot actually, this is not a problem of removing boxes. Okay. So this is what is saying that we are actually printing. So the printer is a very strange printer. So whenever you give a command for it to print, it will start printing a letter and it will keep on printing to the end. So once it is printing A, it will only print A, right? So,
Okay.
and then if we go for a second time, if we want to print B at a particular location, so it will start for that location and keep on printing B till it finishes that turn. Okay, or maybe if the command, in this case, the command is given to print only B at position 1, right?
So
So,
had this been AB, then the second output would have been BBB, right?
No, no, 1 second. Harshit, can you go back to your question on 2As? How will you print 2As?
So the way I thought of this is that it will skip any other character when it tries to print A.
No,
So
that is not
in that sense,
what it says, right? So if you print A 2 times, then it will be the first and the second character or the second and the third character. And that neither of which we want, right?
right.
Like the worst case scenario here is you can print 1A, you can print 1B, and then you can print one more A, and that will be 3 turns. Okay.
Okay.
The second option is to essentially print 3 A's and then overwrite one of the A's with a B, which is the middle one, and that is 2 turns only. Okay. So the way this works is you can, like, making it print continuously from any start location to any end location is considered 1 turn. Okay.
Yeah.
So if you had, for example, let me ask you this question: if you have like A B A B A B A B 10 times, then how many turns will you need?
AB.
Like there are 5 A's and 5 B's.
2 turns.
No, A B, right? 2 turns won't
Yeah,
work.
it's alternate. So you will
The first thing
require
you will
6
do
turns.
is you will definitely use 1 turn for printing all A's. Okay.
Okay.
Then you will essentially go and replace the in between B's. The 5 B's you will have to replace.
Okay.
Right? So there will be 6 turns. That is the correct answer. Make sense?
Yeah. I got it.
So let's make sure we understand the problem correct, because I think this problem is very, it's similar to other problems, but
Hey, Vivek,
subtle differences, right? Go
can
ahead.
you explain that again? Why is it 6 turns?
It is 6 turns. Actually, Santosh, can you explain that, because you have the screen, right?
So
Can you explain
yes.
that on the screen?
So if you see, if this is our input, right? So if this is our input, like A B A B A B, right? So now my first time it will start printing all the A's, which will cover up this location, right? So then this the second turn, it will go and print only one B at one location, right? So this will be my B, right? So this will be my second turn, and second time it will go and print B at this location only. And the third time it will print at this one, and so on and so forth. And this will be the fourth time. So because what it says, the requirement is whenever the printer starts printing, it will start printing at one location, and then it will keep printing the same value. So if it would have to print B's all together, okay, then it will again override. So we'll have all B's over A, right? So we won't have that, what the input is. So we would have something like, if we had printed all the B's on it, okay, same thing. So our answer would have been something like A, B, 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 B. So, but that is not what we want. We want A, B, A, B, A, B.
How do you print B? You have to say, okay,
so it will be
at this position and end at that position, right?
Yeah. So in this case, we cannot separate, right? So we just print at one position and that's it. Because if we try to join these two, because we have a in between. So either we join all A's or we join B's. Okay. So when we join all B's, then we have to separately print all the A's, right?
Okay, so I think basically just let me know if my assumption is wrong. So either you can print a particular character for the length of the string, the same one, or you can say in one position go and print that letter just in that position.
No. You can print a string continuously from any starting position to an ending position, but it will be continuous. So both the cases you said are true, but there is also more cases available, right? You can print from
Right.
the second letter to the seventh letter. You can print from the third letter to the fourth letter and whatever.
Okay, so basically
But it will
start
always be
position
continuous.
remains fixed, and either it will be just in the start position or all the way until the end.
No, that is not right. You will specify a start and an end position both.
I see.
Right.
Okay, cool.
Each turn, you will
Thanks.
say that from the 7th location to the 12th location, fill it with A. That's all you can say. So you will specify the letter to fill, the starting location and the ending location.
Yeah.
So now we come back to the first question. Let's say can print 2A. That's allowable, right? Because you can print 2A, but you know,
but from where to where? In the question that was given on the left, right? Example 2, if you print 2 A's, then you will print the A from the first and second letter, or it will be second and third letter. That's all you can do.
yeah, the first to the second.
The first and second is not useful, right? Because you need to then, when you print B, you will overwrite the A that you printed.
Yeah, that's true. That, you know, get more operation, but the operation is allowed. You can
Oh yeah,
print.
of course. That is not the best answer, but yes, that is definitely allowed. You can print, one of the easiest examples will be to print 1A, 1B, and one more A, and that is also allowed.
Right.
But that's also 3 turns. If you print 2 A's, then print 2 B's, and then print 1 A, that will also all be allowed. Right?
Yeah.
The first 2 A's will print A and A in the first and second location. The 2 B's will overwrite the second location and it will print new B in the third location. And then the third operation will print the A will replace the B with A in the third location. That is also an answer, but it's still 3 turns. So, but you can do it with 2 turns, right? So that's better.
Yeah. So this way, right? Yeah.
Is the question clear? I know this question is a little tricky, so I just wanted to make sure we understand the question.
Yes, exactly. So I'll go through by one note also. There might be some more things. Okay. Yeah. So yeah, this one what we were discussing, right? Okay. So this ABA, this problem. So we can actually also, separate this in these 2 cases what we were discussing earlier. So in the case 1, actually I can print 1A first, okay, and then the remaining will be BA, right? So my first turn will be just A, okay. Then I just print B, and then what is remaining is A, okay. Then that will be my another turn, and then what is remaining was A. So I just print A, and now nothing is remaining. So this is my one more turn, and therefore the total turns are 3. Okay, so the same way what we were solving, so we can also solve this problem that route. You can take whatever is there, use a sort of DFS function here, but in this case, earlier we were actually multiplying with those 2 values. Here we don't care about how many A's were before B in this case, but we just say, okay, we print all of them, so it will be 1, okay, and then we just pass whatever is the remaining in this recursion function, and then it will do the magic here, right? So that this will actually take care of case 1, but if you look at it, the value what we are going to get is 3 turns, right? But if the same thing if we do for the case 2, in this case I first print B, okay, just take out B and just print B at the first index, and then what is remaining, actually it is AA, right? So but if you look at it, it comes to like there are only those 2 A's which are remaining, but we still, because there will be an empty space in between them, but if we want to connect them, if we connect them together, because we have to take care of a single turn, and there are no dependencies on it, right? So therefore we can easily connect them in this case at least. So that we'll have 3 A's, and these 3 A's can be actually printed in the second turn. Okay, so in this case I'm just returning 2 turns. So for me here, actually this DFS will be something like you have ABA, okay, and then you will actually divide this problem again, right? Okay, so this problem will be divided again into 2 sub problems. And I think we'll go to the implementation, things will be slightly clear. Okay, but before that, if we look at, this is just one explanation.
But Santosh, one quick question. In the case 2, you cannot print AAA, right? Your B is going to be overridden. So in the row number 2, so let's say that you print B, right? So you cannot print AAA. So if you're printing AAA, then your B got overridden, right?
Okay, so let me actually do it,
Yeah, you first print AAA and then you print B at that position.
Right, yeah, that's correct. So I was just trying to separate it. So, but yeah, that also is correct. So, okay, so that is one more diagram. I just took it from the net, So it is about these. So we have the same problem here, ABA. So again, we go through each and every index, like we start with A, then we go with B, and then we go with A. Okay, so we follow all the cases. So if we start with A, okay, so then we print A, so what is remaining is BA. So I was just explaining, right? So exactly the way that it is. Again, it is going here, and then I first printed A, then I print B. So what is remaining is A, and then at the end I print AB, A. So now I've done 3 operations in this case. So there are 3 turns. So for this also, if you look in this path, so first I print A, okay, and then what is remaining is BA. So what it's saying is take out the B, take out the A and put B. Okay, so the remaining now will be BB instead of BA. So you can print BB, so that is your second operation, and then replace the last B with A. Okay, so that is your third operation. So this will be ABA. Okay, this is also one way of doing it, but still the operations are 3 in this case. But if we go and look for this, the middle one, if we take out the B and put a A on that, so that is what I was saying. So the remaining will be AAA. So you print all these 3 A's. So that will be done in a single operation, and then replace the middle A with B. Okay. So that is your second operation. That is the most minimal one. So this is ABA. And similarly, you will have to do for the last one also. Okay. So in this way, we are exploring each and every possibility. We have to explore to find the most optimal way. And if you look at the DFS, the recurrence relationship or the function will be something like this. So you can find whatever is the max between like DFS A plus DFS B, or the DFS AAA or DFS B, that is the second one, which is the case 2. Or we can have like the DFS AB and DFS A. So in this case, this will be another case 1.
It will be minimum of, right?
Oh, sorry. Yeah, I'm actually copying the same one earlier. So this has to be minimum. You're right. Yeah. So whatever is the minimum of this, you'll return it. And in this case, this will be the 3. Okay. I hope this is clear, right? This is almost the same what it is about the previous problem, but only in this case, we are not allowed to remove something, but we have to inject, or we have to form something, or whenever we want to bring 2 similar characters together, either we find there is some common space or something which we couldn't avoid, and then we join them. Like here we are doing it like with AAA. Okay, so I'll just show you the implementation. This can easily be done by the earlier implementations. Okay, so even the brute force can be done. So what the brute force I'm trying to do, okay, I'm trying to do the first brute force exactly the way I did for the remove boxes. So remove boxes, I was trying to remove the boxes, right? So I'm just going in this, traversing the whole array. Okay. And when I'm traversing this array, so I'm going and counting all those similar ones. Okay. I'm not counting, I'm actually just incrementing my J index here. So I'm starting with I, and my J is I plus 1. Okay, so the next one, I'm just trying to see if they are same and then increment my j. And then I form a substring where I remove all these values, okay, between I and j, okay, whichever are of the same size, same characters. And then whatever is remaining, I just pass on to this helper function, and here actually just add 1 to it and then get the minimum. So it is the same way what I did for the remove boxes, where I was removing a box and adding the square value to it. Okay, but this is again going to be an O factorial, time complexity, and also the space we are actually using, constructing the strings, right, for each and every recursion level. So that would not be efficient. But if I break this problem in this case 1 and case 2 approach, okay, so this also can be easily done by that along with the case, though we can actually look at again how to, optimize it and for this particular problem. But let's go with the first implementation. I just copied the whole thing as is. I'm just using the helper function with string instead of an array of integers, and then this integer, the I and n, these are the left and right values, and this is my k. Okay, I'm just using all this. Even the base case is the same. Even this case is also the same. I'm just comparing these two positions of in any integer, and then I'm incrementing my k. Okay, and then this is my case 1, where I'm using this helper function. I'm starting from I plus 1 because I finished with the same color, same, not the color, yeah, the same characters. And then the k is 0 in this case. I do all that stuff, and also for the case 2, I keep on comparing and finding if I find anything which is similar in the other portion, and then I try to break down into 2 sub problems. If you look at the index values, indexes also, these I, M, these are exactly the same. But what is changed here is, like, instead of the square value, I'm just adding 1 to this, and I'm trying to find a minimum. That's the only 2 changes what I've done, right? But if you look at this, won't be very efficient also, right? Because in our case, we are actually not required to do with the k at all. Correct? We can actually do without the k. So the other way, what was suggested also in most of the problems, they say that if you have a input like this, A, B, B, so it doesn't make sense to keep on carrying with the whole thing in your recursion. So you can actually shrink this. Okay, you don't mess with the order, but you can string. Like if you have 3 A's, you just make it 1A. If you have 3 B's, make it 1B. And if you have 2 A's here, you just make it 1A, right? So if you shrink that the string in such a way, because the results won't matter here, right? They will be the same. But what you are trying to do is you are trying to prevent the computation. So now you are actually reducing your problem size, okay? And in that case, you just go to the helper function. Now I don't need the k at all, okay? And then, so now if you look at this solution, it looks very neat and clean. So this is only base case, and I have eliminated the while loop over here where I was looking for the duplicate, the close characters. And then I'm just using a helper function with the start index of 1, I plus 1 now. Okay, because now I just have to look for one index, and that's fine. So I plus 1 and j. And here actually I look for if there are any other ones which are of the same, but they are not close to each other. Then I break down. So break into 2 different sub problems here, right? So if you look at these index, they remain the same, but I don't use any k in this case. So now this becomes a normal implementation. What I think, if you look for the matrix chain multiplication and other problems, they are also using similar, but they don't have these conditions here, what we are having. Okay, so those problems might be slightly simpler in some ways. Okay, and this the case 1 and case 2 remains same. And if we add memoization to this one, okay, Okay, so this is, if you add memoization, okay, so then we are good with a top-down approach. So nothing changed here. So we are just adding a memoization, which, so in this case now the time complexity will reduce by 1n. So it will be O(n) cube. Okay, so because so that even the bottom-up approach will be now much better. Okay, so if you look at this bottom-up approach, it again uses only n square. Okay, this is not one. Yeah. So this is the one. So it is also using only a vector of 2 dimension, right? And then we don't have to take care of the k. So here it's only the diagonal values are being filled, initialized with value 1, and then the rest of the all logic remains same, right? You start with 1 1. You start with size 1 all the way to n minus 1, and then construct I and j. Okay, so if you start with a b a, okay, so if you look at this one, you will get 3 because this is the case 1, and in this case 2. You just keep on finding if your m, which will be running from whatever the value is, means it in this case it will run from 1 to 2. So whenever it finds a similar one, the same thing what we did earlier, right? So again, it is breaking into 2 sub problems. One is this b and a. So in this case, what it's trying to do is just ignoring the first a, because we are only concerned with only one a to the end. So as long as we have that a in place, we are good. So we are going to count it, right? Because it's a minimum one, right? So we just count only one a. Actually, there also we are doing the same thing. We are just carrying our k along with our each and every dp value, dp location of that particular matrix, right? And then in this case, you return min, and that's all for this k also. So if I just print it, and if you look at this problem solution, okay, this can be printed. Okay, so if you see here, now the difference is in this case, so these are again the columns and these are the rows, and we don't have those KKs here, right? So they are only single values now. So all these diagonals are initialized to 1 1 1, right? So, but now that what we have to do when we go for length is equal to 1, so in this case, the length will be 0 and 1. So this is our first case where you will take 1, and if both are of the different values, like here, even though it is a b b a, I'm shrinking it to a b a. So therefore, you are having a size of only 3. Okay, so then you just add 1 to this, and then you will get this value 2 over here, right? So this will actually come from yeah. So this will come from here, right? So this 2 value from the case 2 in this case. The same thing will come for, this will be for 0 to 1 and 1 to 2. But when you come to this 2, from 0 to 2, when you're traversing, so you find the first a and the last a, they match. And that is the reason you are not getting a value 3, but you are getting a value 2. Right? So in this case, it will be this value, which is the value at 1 1, row 1 and column 1 added with row 2 and column 2. So these two, if you add 1 1, so this will give you value 2. Right? So this, because this here you are breaking this one, and that is the reason if you look at this equation here, so you'll get these 2 values and your answer will be 2. Okay. Any questions on this one? Or is it not clear? You want to take some more examples? Hey, am I audible? Right, I'm audible, right?
Yeah, we can hear you.
Yeah, okay. Yeah, so this is okay, right? So because both the problems were almost similar in nature and you could use the same implementation, but the remove boxes was slightly on the difficult side than the strange printer. But just wanted to go with the remove boxes first, because if you understand the critical one, then it's slightly easier to understand the second implementation, right? So that is the reason I took that approach and that route. Okay, so do you want us to go to the last problem also, or?
Yeah, let's go to the last problem.
All right. Well, folks are in shock or something.
I don't know. Yeah, that's
super interactive till now. So I was just surprised what happened. Do people want like a couple of minutes break before we get the next problem? Maybe that will help. Go ahead, Santosh.
Okay. Yeah, thank you. So this problem is about burst balloons. Okay. So this is also a very famous problem. I've been seeing it discussed many places on the internet. And here it says like you are given balloons which are indexed from 0 to n minus 1. There are n balloons, and so each balloon is painted with a number on it. And so you are asked to burst all the balloons. So if you burst a balloon at a location index I, so you get points by multiplying its left side and the right side. So whatever the numbers on the left side and right side, if you multiply all those three together, and that you get that many number of coins. Okay, and then here what they say, left and right are the adjacent indexes of the what I which you just bursted. And so after the burst, the left and right becomes adjacent. When you burst I, so you are actually just like the remove box, you're removing that balloon, and so left and right will become adjacent. And here the goal is to maximize the coins that you can collect by bursting the balloons. And you say you have to do it wisely. Okay. And also he's saying when you are at the edge, like if you see this example here, so when you want to burst a balloon 3, but you don't have anything on the left of it. So in that case, he's saying you just imagine that value is going to be 1. And the same thing applies for the right side when you're bursting a balloon 8, right? So the right side of 8 will be again 1. Okay. So they are not the real, but you can just take those values. And if you look at the notes, it says you can have 0 to 500 such balloons, and then the colors can be from 0 to 100. Okay. So here, this is the input. If you have 3158, and then how do we arrive at this value? It says they are following a very special way. Okay, so the first, if you burst 1, then you actually go and multiply 315. Okay, so at that time I will be removed, then the array will be like 358, then you burst the 5, and then you'll get 358. Okay, and then keep on doing that, so eventually you will get 167. Okay, so there are slight tricks in understanding actually which one to burst at a time, but if you keep on doing that, again, this is also a recursive way to do that. We have to explore all the options. Okay, so then only you can arrive that. And okay, so let me actually go to my OneNote. And okay, let me see what I have something over here. Okay, there's not much here, I think. Yeah. Okay, so here, okay, so I'm actually taking help of one of these diagrams which I found on the internet. So for this one, what it says is if you have 3158, again, you can do the same way, like you start with 1, or index 0 or index 1 and index 3 or index 4. And when you are doing that, but here in this case, there is nothing like case 1 and case 2. Okay, so that's the way it is different over here. But then when you burst 3, so what you are remaining with these 158, and then so you actually, if you burst 1, you will have 58. Okay, and then you actually go again. So here, the more it's trying to show is the representation of an overlapping subproblem, right? So if you see, that is 58 over here, as also the 58 is used over here, and then you have a 18 here, 18 here, same thing for 38, 38. So it is like a overlapping subproblem. So that is what it's trying to say. If it's a sort of a DP problem, if you can solve any of the subproblems optimally, and you have your optimal substructure, so it solves your problem optimally. So that was satisfies your DP, right? So you can very well use your DP implementation to do that. Okay, so in this case, the way the brute force would be exactly for the remove boxes. Okay, so but the only thing is we need to take care of the left and right side. Okay, so here also, if you have a numbers array and you go through each and every index, and when you're going through each and every index, you have to shrink that because you have to burst one balloon. So here I started with saying, okay, I'll burst my balloon at location 0. Okay. Okay, before that also, I am adding 1 to the beginning and 1 to the end in this case, and I'm actually increasing my value. So I'm padding the start and end. So I don't want to get into that problem. Oh, I'm sorry. Yeah, not here though, right? Okay. Yeah. Oh. Okay, so the first one I did not actually pad. So okay, so here what I'm trying to do is I want to shrink it. So before that, I want to burst one of the balloons which is at high index, and to take care of this the edge cases, I have to do it this way. I set a left and right variable and then look for if it is greater than 0, then only I take my n-1, or if it is less than. So this is just trying to take care of the edge cases, right? So whenever I'm trying to burst a balloon at 3 or 8, correct? So therefore the whole thing I have to do here, and in this case, so whatever is remaining, okay, if I bursted one balloon at a particular location, I go to the beginning and remove that from my array. Okay, so it's like I'm shrinking here, and then at the end, I do the same thing. I pass to this helper function, and here we have to multiply left, right, and the num psi. Okay, so if we multiply that and then add to this helper function, so it is almost the same if you look at and if you understand the previous two approaches. So this, at least the brute force looks the same as that. Okay, but now this can be actually this is slightly cumbersome, right? So always having that. So one way I found which was good is, you pad those the first and last values. In this case, just take this nums and then insert 1 to that and also push back 1. So now your array, instead of 3158, it will be 13158, and it will increase in size from 5 to 7. Okay, so then just start the same helper function here, and so this is the left and this is the right. And here the base case will be like if I have left and right, they are consecutive to each other. They are so that it means that there is no balloon in between, right? So that is what the base case is. Or else you just start from your left. Okay, so left plus 1, because your left actually has one value which is a padded value. We don't want to go and burst that value because that is not useful. And then you go to right -1, because the right value is also actually the padded value. And then if just find the maximum value, of whatever these two things are, okay, because you're actually breaking down in two sub problems here again. It is slightly similar to that problem because we are just breaking down. We are not using any case 1 and case 2. In this case, whenever we want to burst a balloon, so in this case we are bursting a balloon at m, okay. So therefore what we do, we burst a balloon at n, and then we just get our values by multiplying the left and right, and just pass on the left and m, as well as here for the second sub problem, pass m and right. So why m? Because I'm bursting m, I'm still passing m, because if you look at here the right, and if you look at this value, I'm taking value I'm just going through light minus 1. So that is the reason just passing m here. Okay, and same thing for left also, because I'm starting from left plus 1. So those edge cases are taken care of. That is the reason it's been broken into sub problems as left to m and m to right. And then if you keep doing that, and then you find whatever is your maximum, you can return. So if you look at the way it was explained in the discussions, they say like if you go and break the array, and if you burst a balloon in middle, so that you'll form two different sub arrays. And then if you are to suppose the two sub arrays, if you burst the first array, the rightmost balloon, so you're not sure what will be on its right side, because the two arrays are now side apart, right? So that is the reason, if you see recursively what we are trying to do, we are going to the base condition first, and instead of actually bursting from top to bottom, we are actually adding balloons here, right? So we go to the base condition, and from that we keep on adding, and then when we go to the base condition, we know we are at the right and left. Okay, so therefore if you see this right and left, and we just add whatever is m, at that time that is the only one value or that balloon we are adding. So it is the reverse way we are doing, and that is the best way to do as per the solution also. So because then the adjacency of the right and left is taken care of in this case. But this happens by this way of implementation, and it happens unknowingly, so it is a good fit for this one. Okay, so if we just memorize this version, we actually get a top-down approach. Okay, so then we have this memo version here. We add this memo, and it is also a two-dimensional array. And then we are storing the values of left and right. Okay, so we store the values of left and right, and whatever this has been written by this max function is being stored at these places, and then we return. So whenever we don't find any value of, if the value is greater than -1, you return this, or else you store this value. Right, so this is the top-down approach. Okay, and the bottom-up approach is also almost similar to here, and so this will be here we don't have to do any base case. Okay, so this is the DP array, and then but we start from a length which is equal to 2. Okay, and then again set I and j, these two variables which we want to break down these into two sub problems, and then start from m, from which will start from I plus 1 and j, and then keep on doing this, right? So if we quickly look at one of the implementation, okay, so if I just print this one, yeah, so if we have this 3158, if you look at this one, so this is what the or the DP array looks like. And we have these two columns and two rows which are zeros. The reason we have padded with two values, right? So 1 1, and therefore these two are zeros, row and column. And the real actually is from 2 to 5, the columns, and from the rows it will be from 0 to 3 only. That is what the whole real thing is. So if you see, if you look at the 2, so then the way it is implemented is, so here actually we want to break 3, right? If you look for 0 and 2, so this is what we want to burst the balloon at, which is 3. So if we burst the balloon 3, so you will look at the values at 0, 1. In this case, this is 0. And also you will look for the other subproblem, which is the value 1, 2. Okay, because this is 0, 2. So then you have to look for value at 0, 1 and 1, 2. So if you add those two and then multiply 3 with its left and right, in this case, it will be 1 to the left and 1 to the right. So you'll have 3. And if you go for the 15, so this is the way the diagonal values are filled in. If you go to 15, that is 1 and 3. Okay, so 1 and 3, you can add 1, 2 and 2, 3. So these both are zeros in this case, and then multiply. In this case, it will be 3, 1, 5. So therefore, this is 15. Okay, so then you keep on doing this for the diagonal values, and again, the same procedure we'll have to follow. So start with the length of 2, then go for length 3, length 4, and yeah, I think it is length 4 max, right? 1, 2, 3, 4, 5. Okay, till length 5. And so at this length 5, so it will again follow the same. It will keep on looking for the two adjacent ones, but for 167, if you see, it will start with the value from, I think it will start from 0 to 159. So it will start from 0, I think 02 to 1, 02 to 15. No, sorry, it will start from 01 to 15. And then it will go from 0 to 225 or 02 to 35. These two values will keep on adding, and also you'll have to multiply the left and right along with the value of this current balloon what you're bursting, and then you just find whichever is the maximum value, and that value you assign it to this particular location of 0, 5 or so. I think that's what in a nutshell. I can actually post all the details of how to look for and how to go in this, this particular metrics. And also I have one, I'll just quickly share that. So this burst balloon. So there is a lot of, so if we look at this DP array, and if we have this input array as 318, and we are adding 1, 1 to both of them, so it is 1, 3, 1, 5, 8 now. And our DP array, which is, these are the columns and these are the rows. So how these values come, and if you look at the exact the way what the implementation is broken down, and so this is the way, like you start with I 0 and j equal 2, and then m equals 1, and then keep on calculating all these values. So each and every point. So this is the 3, 15, 40, 40. Okay, so that is, so if you look at this one, so it is 3, 15, 40, 40. So this is for the length 2, and if you look for length 3, so which starts from 0 to 2, 0 to 3, and 1 to 4. So these are the values of 30, 135, 148. So how I have arrived at that. So these are the values. So if you take 30 and 5, whichever is the maximum, you will just set it over here. The same thing be done for the next one, 65, 64 and 135. So 135 is on the higher side. So therefore 135 comes here, or then 48. So the same thing actually keeps on repeating for length equals 4. Okay, in this case, how this 159 is arrived is like, because this is the maximum value out of these 3 combinations. And same thing here also, this was 159, and then you take length 5, you'll have to do for each and every location. So if you look at just going from 0, 1 to 1, 5, 0, 2 to 2, 5 and all that, and then at the end, this is 167, which is the maximum, and that is the reason we will be looking at this 167 as our output, right? So this is the whole calculations that's been done. It's actually done in that algorithm implementation, right? Yeah. So I can post this. I don't think it's worth explaining here right now, right?
Thanks, Santosh. This was really good.
Okay, thank you. Yeah.
Thank you.
Thank you. Yeah.
Thank you, Santosh.
Yeah, thank you. Yeah. So I'll just close the recording, right?